So the energy generation method, which is renewable, is pump storage. And the reason is that it can be replaced in a short time scale. And the others, that is not possible. Okay, in a nuclear reactor, outline the purpose of the heat exchanger. Here we need to indicate that it transfers heat from the reactor to the water in the cooling mechanism. And that will turn that water to steam, and then that heat will be released. And the important word we want to include here is the word transfer. We must have that in our answer. Okay. The idea of the moderator is to slow down the neutrons so that they're better or more likely to be captured by the uranium-235. So we need to say two things. Firstly, to slow down the neutrons. And secondly, to increase chance of neutron capture. So the neutrons are moving very quickly, and if they are doing that, they're less likely to be absorbed by the uranium-235 and become uranium-236. So the job of the moderator is to slow them right down so that they can then be captured or absorbed by those uranium nuclei and fission can occur. Okay, so here we're told that fission of one uranium-235 nucleus releases 203 MeV of energy, and we want to know the maximum amount of energy in joules released by 1 gram as a result of fission. Okay, so we can use the moles equation here, and we can say the number of moles is mass over molar mass. And in this case, that's going to be 1 gram over 235. Remembering that for this equation, this is the one time we work in grams and not in kilograms. So we have 1/235 of a mole, and we know that 1 mole has 6.02 times 10 to the 23 nuclei. That's Avogadro's constant. So we can say that here we have 6.02 times 10 to the 23 divided by 235 gives us the number of nuclei we have. That comes to 2.56 times 10 to the 21. And each one of those nuclei is going to release 203 MeV. So we times that by 203. That's still in MeV, and we want our answer in joules. So we then need to convert that into joules, and we can do that quite easily by timesing by 1.6 times 10 to the minus 16, because it's MeV, not EV. Okay, and when we do that, we get an answer of 8.32 times 10 to the 10 joules. Okay. Specific energy of coal is 2.8 times 10 to the 7 joules per kilogram, and they've given us a nice hint here in case we forgot or the difference between specific energy and energy density. They've given us joules per kilogram. So the ratio is, or the value for specific energy is energy per unit mass. So here we have to do that for uranium, and we can calculate that by working out the energy that we got from 1 gram, which is 8.32 times 10 to the 10, and then divide that by 0.001, and we're back into kilograms now. That's why we've written our 1 gram as 0.001. Okay, so we can do that and then divide that by the specific energy of coal, which is 2.8 times 10 to the 7, giving us the ratio, which is 2.97 times 10 to the 6. Part 3, using the answer to C part 1, outline why fossil fuel stations are often built near to the source of the fossil fuel, but nuclear power stations are rarely close to the source. Okay, so thinking about what was asked previously, we can see that the energy, the specific energy of coal is quite low. In other words, we need a lot of it in order to get this comparable amount of energy to uranium. That means it's going to cost a lot of energy to transport all that coal, so we can say that there are large transportation costs. For nuclear power, they don't exist in the same extent. However, we do need to keep it safe, so we want to keep nuclear power away from human settlements, and we should specify here for coal. Okay, and that is the end of the question.